Hello and welcome to the 16th lecture of our graduate combinatorics course. Today we will discuss another method of counting, which is called enumeration under group action. Before we start the formal definitions and results, let's just go over some examples that may seem unrelated to each other, which involve we'll see later, will involve this method. So in the example 0, the question is, in how many ways can we color the sides, the 6 sides of a regular tetrahedron with 3 colors? Of course, the 3 colors can be changed to whatever number of colors you wish. In the example, in the pictures over there, we have 3 colorings in which we use 5 purple colors and 1 gold colors. And all these colorings are considered to be the same because we can rotate or translate, move the tetrahedron around to get it from one picture to the other. So the question would be, again, in how many ways can we color the sides of a regular tetrahedron using 3 or whatever number of colors we wish? The second example comes from number theory, and it's the famous Fermat's little theorem, which states that if p is a prime and n is an integer, then p divides n to the p minus n. The second example there is Cauchy's theorem from group theory, which states that if we have a finite group and we have a prime divisor of it, then G must contain an element of order P. And the last example that we have is somewhat similar to the first one in the sense that we have a clear counting problem, and we're asked what is the number of necklaces of n beads where we have, let's say, lambda choices for each bead. So in this situation, 2 necklaces are the same if we can modular a circular shift. So if we can shift the beads around, and we can get 1 necklace from the other. So let's get started. Before we talk about group actions, let's give a quick reminder about groups. So a group consists of a set, usually denoted by G, and a binary operation, which is sometimes written in multiplicative notation, as it's done here, and sometimes it's written in additive notation, in which case it's written with a plus. So we have a set and a binary operation, and this binary operation satisfies 3 properties. This operation is associative. So let me put it with the right green color. Associativity. So the first property is that G times, so there should be a times here, G times H times K. It doesn't matter in which, the way we put the brackets around them, we can calculate it either as G times H and then times K, or we can calculate it as H times K, and we multiply to the left by G. The second property is the existence of a neutral or identity element, and it states that there exists an element. In the multiplicative notation, it's usually denoted by 1 or 1 of G if we want to make sure that we specify the group to which it belongs. And this element has the property that G times 1 of G and 1 of G times G equals G for any, this happens for any element G in G. And one can show, I won't do it here, that this element is unique. So that's why we call it the identity element or the neutral element for this binary operation. And the third property of in the definition of a group is that every element has an inverse. So for any G in G, there exists an element H, which depends on G, such that G times H equals H times G equals the identity element from part 2. And this H also can be shown that is unique. Given a G, there exists a unique such H, and it's usually denoted by G to the minus 1, and it's called the inverse of G. This is all in the multiplicative notation, as I mentioned. In the additive notation, if one uses the notation with G and the operation with a plus, then the 1 of G is usually denoted by 0 of G, and the inverse, instead of being written as g to the minus 1, is written as minus g. Now, let's move on to the next definition, and that's the definition of a group action. So for a group action, we need two actors, and the first actor is G. We have G, a group, and we have X, a set. Now these groups and sets don't have to be finite, but for us, in most of the cases, they will be finite. And now, what do we have? We say that G acts on X if there exists a function or map from, I'll just use the same dot, which sends an order pair where the first element is from G and the second from X to X. So I'll write it here. We get G comes from G and the element X comes from X. This gets mapped to G. I'll use the same dot, but be careful, it's not the same dot from the operation on the group, okay? With the property such that we have two properties. If the identity element acts on X, we get X back for every X in X. And two, if H acts on X and then G acts on it, this is the same as G times H acts on X for any GH in G and for any X in X. So just to avoid confusions, we use this dot in the definition of the group, but other than in the definition, the notation for, like, if we have two elements in G multiplied by H, it will be denoted by GH. Okay, so from now on, and we'll see, in some cases we will even omit it for the group actions once we get more familiar with it. We will reserve this this dot notation for this map, which sends an order pair of a group element and an element of the set to an element of the set and satisfy this property. So again, here we say that the group acts on X, and in this situation, like part one, in that situation we say that the identity element of the group acts on an element X of X, and the resulting result is X itself. And in the second property, we have this relation between the group multiplication. So we have two group elements G and H, and with the action of GH on X is the same as the action on G on the action on H on X. So let's move on and see some examples and kind of go into more details about this notion. So I wrote here on the top right, I wrote the definition again. We have that G acts on X. If we have this map, which takes an order pair of a group element and an element of X and maps it to an element of X, and the two properties that we just discussed. So first is the simplest example of an action, which is called regular action. And if that's the group, it acts on itself. So we take any group G, and in this case, X equals G itself, and we can define the map G acts on X, and the result is the multiplication GX in the group. And yeah, we say again, G acts on G via multiplication. We have to specify this because we'll see that G can act on itself in different ways. And let's check that this is a valid group action. Well, we have to check the two axioms. So the first one is that the identity acting on X, well, this is going to be, by our definition, the product of the identity element times X, and that's X itself. So there's nothing to prove there. It's very, very easy. And then the second axiom, the second property of the definition follows from the associativity rule of the operation on the group. So G acting on H acting on X is G times H acting on X. In this case, all the dots are operations in the group, so it all goes as planned. Okay, so let's do something, another example now. Let me use a different color. Let's say we have, again, G is a group, and we have H, a subgroup of G. And now we take the collection X as being the collection of all left cosets of H. So it's all sets of the form A times H with A in G. So X consists the family of left cosets of H. Okay. So in this situation, we can define the function, and we'll see that it's a group action. So we define it as follows. Again, we go from G times X to X. We take, so from here, we take a group element, G, and we want to see how it is going to act on an element of X. An element of X is of the form AH. That's a typical, like a coset. And we define this, we define it as GA times H. It's the coset of G times A. So this is for every G and A G. And we claim that this is a group action. Okay. And again, to show why it's a group action, we have to verify the two axioms. Okay, identity acting on some arbitrary coset by the definition above is the same as identity times A times H, which is the same as AH. So that works. And then the second one is G acting on H acting on AH. What will this equal? Well, first, let's leave the G alone, but H acting on A, the coset, that's going to give us HA, H, and this is going to be GHA times H. So it's a coset of G times H times A, which is the same thing as the action of GH on AH by our definition for any GHA in the group G. Okay, so that's an example of a second action. Let's do a third example. This is again G, a group, and X is the group itself. And here we will have an action G acts on itself via conjugation. Okay, so let's define the following function from, so we'll define this function from the Cartesian product G and X to X. And how is this going to work? We take a order pair G and X. So here, both the elements are from G, and we map it to the conjugate of X with respect to G. So it's GX, G minus 1, which is an element of, so G is the same as X. Now, so we have to argue what, we have to prove why this is a group action. Okay, and why is that? Again, as before, if we take the identity and we act with it on X, well, what do we get? By the definition, is going to be 1G times X times the inverse of 1G, but this is the inverse of the identity element is the identity element itself, and multiplying by the identity element doesn't change anything, so we get what we wanted. And then the second one requires a little bit of care, but is not too hard. So let's say, what is G acting on H acting on X? Well, this is G acting on H minus 1, and this is the same as G times H times X times H minus 1 times G minus 1. And this part can be rewritten as GH times X times the inverse of GH. And this is the same thing as the product GH acting on X for any GH X in G. Okay. So the group, we saw two group actions of the group on itself, one by multiplication, one by conjugation. Let's do another example. Let's take here as our group, let's take P as a prime, P is some prime. And G will take the integers modulo or modulo P, Z quotient P or ZP, so 0, 1, P minus 1, integers mod P. Okay, and the set X for us is, let's say, the set of order P tuples X1, X2, XP, where X1, XP come from a set. So there are elements of the set 1, 2, 3, n, where n is some natural number. Okay. So I have the group, integers mod P, and I have the set, order P tuples, so the same P, order P tuples of a set of natural numbers. And now how does this act on, how does the group act on it? Well, the group is the group G is generated by one element, which is the element 1. And so it's enough for me to show how 1 acts. So I will write the element 1 from the integers mod P. I'll put a hat over them just so that we remember where it comes from. So let me take the element 1 with a hat over it. And you have to be careful here because it's called 1, but it's not the identity element with addition, modulo P, that's the element 0. So I'm defining here how the element 1 acts on a tuple of X1, X2, XP, and it acts by shifting this tuple to the right. So XP comes in front, and then I get X1, blah, 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 XP minus 1. So this is how 1 acts on it, and it's enough for us to specify this fact, because every element in the group can be obtained by adding 1 a certain number of times, and then we just repeat this action of 1 on a corresponding P tuple. So for example, if I wanted to say, let's say P was greater or equal to 3, and I wanted to say what is 2 acting on X1, X2, XP, well, this can be done combining the first property and combining the second property of the definition, because 2 is obtained by doing 1 plus 1, and then the first one is going to shift so this will be 1 hat acting on XP, X1, XP minus 1, and this is going to be XP minus 1, XP. So it shifts by 2 essentially, and so on. Okay. So here, so with these things in mind, one can prove that this is also a group action. And I'll leave the details to you. So I'll leave the details for this one. I'll give you one more example, the fourth example, which is similar to this one. it's not necessarily, you know, there's nothing special about P over there. You can do a similar action as follows. Let's take n a natural number, and let's take G to be the integers mod n. So integers mod n. And again, let's write them with 0, 1 hat, all the way to n minus 1 hat. And here, the set X is defined as all n tuples, x1, xn, where x1, xn come from a set with 1, 2 lambda colors. So lambda is also a natural number. Okay. And we define the action as similar. So let's just write it with a hat, 1 hat acting on x1, xn is defined as shift to the right, xn, x1 all the way to xn minus 1. And this, you know, using with this definition, we have also the definition of how the second element and so on acts on an n tuple and so on. Okay, so I'll leave this one as an exercise to prove that this is a group action. Okay, and the same thing. It's same thing here. Now, as you probably guessed, if you looked at our examples at the beginning, this example 1 here will be related to the example that we did, the group action of integers mod p acting on these p tuples or elements from 1 to n, and the example 3 will be related to the number of necklaces, with counting the number of necklaces, and beads or lambda choices will be related to the last example that we did here. But we have to do a bit more work until we get there. All right, so these are our examples. So let's prove some results. Okay. Now, the first one, it's a bit of a theoretical result. So let's say let G be a group acting on a set X. Then the map from G to the set of permutations sim of X on X, with which is a group with function composition defined by G maps into sigma of G, which I'll define in a second, where sigma of G is the function from X to X, defined as sigma of G of X is defined as G acting on X, is a group homomorphism. Okay. So proof. So first of all, for let G be an element of G. First of all, we show that sigma of G is a permutation, is a bijective function. Okay, so what do we have? Sigma of G is defined on X with values of X, and sigma of G of X is by definition G acting on X. Okay. And what do we have to prove? We have to prove that this is injective, and we have to prove that it is bijective. So injective, if we have that sigma G, if we have two values, sigma G of A, well, let's see, I'll use X1 and X2. So let's say sigma G of X1 equals sigma G of X2. Then what does it mean? It means that G acting on X1 is the same as G acting on X2. And now I multiply, I can not multiply, I can act. So each of these elements, G acting on X1 and G acting on X2, are both elements of X. And now I can act on each of them with G minus 1. So G minus 1 can act on G acting on X1, and it's the same thing as G minus 1 acting on G acting on X2. And now by the second property of the definition, G minus 1 acting on G acting on X1, it's the same thing as G minus 1 times G acting on X1. And similarly on the right-hand side is the same thing as G minus 1 times G acting on X2. And now you kind of get the idea why we did this, acted with the inverse of G to the right, because we get now that 1G acting on X1 equals 1G acting on X2, and by the first axiom, it means X1 is X2. So that means that the function is injective. Let's see why the function is surjective. So it helps to write down what we have to prove. We want to prove that for every y in X, there exists some X in X such that sigma G of X equals Y. I mean, sometimes if this kind of bothers you, using X and Y over and over again, you can use different letters if you want. You can say for any B in X, there exists A in X such that sigma G of A equals B. Okay. So in this situation, okay, we have our B. So we say let B be an element of X. And when you prove these things, you kind of have to think backwards. Okay, what should I plug into the function to give me B? So you can do a bit of a side work, and it's not too hard to actually define A to be the action of the inverse of G time on B. Okay, and this is a legit element of X. And then what is sigma G of A? Well, this is going to be, by definition, G acting on A. But what is A? So A is G inverse acting on B, and we do something similar as before. Like the second property of the group action, this is G times G minus 1 acting on B. This is 1G acting on B, which is B. So that proves surjective. Okay. So this function is a legit function. So our map, so that's an important property of the group action, that for every element G of the group, this map sigma of G is a permutation of X. It's a bijective function from X to X. That's what we just proved. And then in order to prove that this map, so the map from G to sim of X, you take G and you map it to sigma of G. This is a group homomorphism. We have to prove that 1G gets mapped to identity element, but 1G gets mapped to sigma of 1G, and sigma of 1G is the identity on X, identity permutation of X, because if you act the identity 1G acting on every X, it doesn't change. So this map sigma of G is identity on X. And the other thing one has to show is that when we, GH is going to get mapped to sigma of G times sigma of H. And that's not too hard, because GH gets mapped to what? To sigma of GH. And I leave it to you to show that sigma of GH actually equals sigma of G composed with sigma. Okay, this is sigma of G composed with sigma of H. Okay. All right, now this result has an interesting consequence, and that is the following. If you take, so I'll put it here. If we take the action of G equals X from before, and and G acting on G by multiplication, then this will tell us that the map G to the group of permutations on G, which sends G to sigma of G. This is a group homomorphism. And it's actually pretty easy to show that the kernel of this map is trivial. And by the first isomorphism theorem for groups, this will tell us that G is going to be isomorphic with the image of this map. Let's call this map phi. And this is a subgroup of this symmetric group, sigma of G. So this proves the result of Cayley that every group is isomorphic to a subgroup of some permutation group. Okay. All right. Now, going back to the counting problems. So when we're gonna work now in general. So we have G, a group acting on a set X. So what we can do here, the objects that are of interest are the following. We can define an equivalence relation on X as follows. X is equivalent to Y if there exists G in G such that Y equals G acting on X. Okay, so this relation is going to be very important for us. Now, I claim that this is an equivalence relation, but that requires a proof. So this is what we'll do here, proposition. The relation above is an equivalence relation on X. Now, as you may remember from your undergraduate classes, a binary relation is called an equivalence relation if it has to satisfy three properties, and those are reflexivity, so X must be equivalent to X. Symmetry, so if X is equivalent to Y, then Y has to be equivalent to X. And transitivity, if X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. So let's write each of them. So reflexive, that means that we have to prove that X is equivalent to X for every X in X. So to do that, we take an element X in X. And what we have to show is that there is some group element G that acts on X to give us X, and that's pretty easy. We have that, we know that X, by the definition of an action, X equals the identity element of the group acting on X. Therefore, this proves. This means that X is equivalent to X. All right, the second property is symmetry. X is equivalent to Y implies Y is equivalent to X. Okay, for any X and Y. G. Okay, so we start with X and Y. Any X and, sorry, here, it's a mistake. X. Let's take X and Y in X, such that X is equivalent to Y. This means, by the definition of this relation, this means that Y equals G acting on X. And now we act on both sides from with G minus 1. Therefore, G minus 1 acting on Y is going to be G minus 1 acting on G acting on X, which is G minus 1 times G acting on X, which is the identity acting on X, which is X. This implies that X is some group element of G acting on Y, so that means that Y is equivalent to X by our definition. And now the last part, which is to prove that this relation is transitive. X equivalent to Y, Y is equivalent to Z implies that X is equivalent to Z for any X, Y, Z in X. Okay, so let X, Y, Z be in X such that X is equivalent to Y and Y is equivalent to Z. Now, because X is equivalent to Y, there is some element G in G such that Y equals G acting on X. Good. Now, because Y is equivalent to Y, there is, let's say, H in G such that Z equals H acting on Y. Now, what do we want? We want Z to be something acting on X. So we start with this equation. So we have, therefore, ZH acting on Y, and then we take the Y from here, and we plug it into here, and we get H acting on G acting on X, and it's H times G acting on X, and H times BG is an element of G, and hence this means that X is equivalent to Z. Okay. So we proved that this binary relation is an equivalence relation, and this is quite an important result. And why is that important? Well, any equivalence relation right here. Any equivalence relation partitions the set into equivalence classes. Okay. So again, let me write it as, rewrite this thing from here. We have G is a group acting on X, and we had X is equivalent to Y, and only if there exists G in G, such that Y equals GX. And we prove that this is an equivalence relation. And from here, so what we can define the equivalence classes of this equivalence relation. These are called orbits of the group action. So for X in X, let me denote it by O of X. This is denoted by everything that's equivalent to X. So this is denoted by all elements Y, Y in X, Y equivalent to X. And of course, from the previous definition, this is the same thing as everything Y in X, such that Y equals G acting on X for some G. And so this can be written also as G acting on X for all G in G. This is the set O of X, which is the orbit of X. Okay. Now there's another, so this is called, like I said, this is the equivalence class or the orbit of X. We'll do some examples in a second, but I need one more to define one more thing. And that's the following. For X in X, we can define the stabilizer X is defined as, so G with X as a subscript. This is formed by all the elements G in G that do not change x. So G acting on x is the same as x. Okay, and now because from the definition of a group action, we know that the identity element belongs to G of x for any x in x. But there could be other elements there as well. Okay. So we have these two important objects. So you have these orbits, which are the equivalent classes of the elements of x, and we have the other thing is the stabilizer of x, which can be defined for every x, and consists of all the group elements that fix x. So let's prove some results about this. Objects. Let G again be a group acting on a set X. Number one, the set of orbits partition X. Number two, the stabilizer, so for any x, G of x is a subgroup of G. Okay, and number three, if x is finite, then the cardinality of an orbit of x equals, can be written as the ratio between the cardinality of G. So I get, well, let's write it like this. It's the index of G of x as a subgroup of G, and if G is finite, this is the same thing as the cardinality of G divided by the cardinality of the stabilizer. Okay. So proof. Well, the first part follows from the results about equivalence relation, and it's easy to prove it for equivalence relation. Is easy to prove it, obviously, for this particular one. But whenever you have an equivalence relation, the equivalence classes form a partition of the set. So the result follows from the fact that the binary relation defined previously is an equivalence relation. So just to remember, we will have always that the following, that x is a union or all x in x of OX. And here in this union, I'm taking just, I don't take repeats of orbits. And we have the following situation is, x is equivalent to y. It's the same thing as their orbits are the same. And when x is not equivalent to y, this is the same thing as their orbits are disjoint. Okay. All right. Now, the part of about the stabilizer is not too difficult. So, to G of x, we want to prove that is a subgroup of G. So what do you have to prove that something is a subgroup? So first of all, that the identity element is in G, so we want, okay, let me rewrite this. So for 2, we want to prove that for any x in x, G of x is a subgroup of G, okay? So to do that, we have to prove, so we pick an x and we have to prove two things, that one of G belongs to G of X, which we already did. And the second part is that if G and H belongs to G of X, then G A minus 1, H minus 1 belongs to G of X. So let's give a quick proof of this. So G of H belongs to G of X, it means that G acting on X is X, H acting on X is X. Now, from the second one here, if we act to the right, if H minus 1 acting on H is X equals H minus 1 acting on X. And that implies the left-hand side, you can verify that's X, and the right-hand side is going to be H minus 1 acting on X. And now we can do what is G times H minus 1 acting on X. This is going to be G acting on H minus 1 acting on X, but H minus 1 acting on X is X, so this is G acting on X, and therefore this is X for any, this is X. So that implies that GH minus 1 is in the stabilizer of G of X. Okay. And yeah, so that's basically the proof. And now let's do the third part, which is that the number of elements in the orbit of X equals the index of G of X in G. So how is the index defined? So we proved before. So we just proved that G of X is a subgroup of X. So we'll take X, an element of X. And now we can look at the cosets. So the cosets A times G of X, A in G of G of X. Okay, and let's say we have a certain number of cosets, and let A1, let's put it like this. Let A1 GX all the way AK GX be the distinct cosets of G of X. So here we also have the following situation. We'll have that G is partitioned into these cosets. So it's A1 GX, disjoint union all the way to AK G of X. Okay. And here, maybe I didn't say it, but A1, AK are elements, AK are elements of G. Okay. So with this notation in mind, it's clear that the index of G of X in G is K. It's a number of cosets, so we have K cosets. Okay, and now what can we say? So we have here G is A1 GX to the AK GX. And what we would like to show is we would like to prove that the cardinality, the orbit of X equals K. Okay. All right. So how do we do that? Well, what do we have? What is the orbit of X? Orbit of X consists of all the elements Y, such that Y equals G acting on X for some G. Okay. Now, so what happens when we have, so this is the same thing as G acting on X for all G in G. So you can think of it, orbit of X, as going through taking all the elements of the group G and acting with each element of the group on X and seeing what elements you see. You may see several elements multiple times, but you just keep one copy of each element of X that you see, and you throw the, that's the orbit. So when do we see, for example, that G acting on X actually will equal H acting on X? When does that happen? Well, that's equivalent to what? That's equivalent if we pick one direction, let's say we can act of, let's say, H minus 1 times acting on G acting on X. It's the same thing as H minus 1 acting on H acting on X. And this is the same thing as H minus 1 G acting on X equals, on the other side, we have 1G acting on X, which is X. So this is equivalent to H minus 1G belonging to the stabilizer of G of X. Okay. So that means this is the same thing as G, the two cosets being the same. Okay. So we have that two elements in this multiset of the form G acting on X and H acting on X are equal if and only if their cosets are equal. So therefore, the number of distinct elements in this orbit is going to equal the number of distinct elements, the number of distinct cosets of G of X, which is K. All right, so I'll stop here and we'll do examples using this result and a few more other results. Next time, I'll just stop to say that this result here, this is called the orbit stabilizer lemma. And it's easy to remember why it's called that. Relates the cardinality of an orbit to the cardinality of a stabilizer.